Recall the following definition. We say that a group G with binary operation composition is called 2-generated if there are two elements A and B in G, which generate all of G. That is, G equals angle brackets AB. Then we have the following proposition. Assume that G with composition is 2-generated. Then G is generated by sigma 0 equals A, sigma 1 equals B, and sigma infinity equals B inverse composed with A inverse, where sigma 0 composed with sigma 1 composed with sigma infinity equals the identity. Assume also that G is a finite group. Then there are positive integers m, n, and k, such that sigma 0 to the m equals sigma 1 to the n equals sigma infinity to the k equals the identity. In particular, there is a surjective group homomorphism, pi from delta of m, n, k to G, which sends gamma 0 to sigma 0, gamma 1 maps to sigma 1, and gamma infinity maps to sigma infinity. Next, we will consider fundamental groups. So let's consider the definition. Let X be a Riemann surface. Fix X naught in X. We'll call the point X naught a base point. And we'll denote by pi sub 1 of X comma X naught the collection of paths gamma from the interval 0 to 1 into X, modulo homotopy, such that gamma of 0 equals gamma of 1 equals X sub naught. So we'll often call such paths that begin and end at the same point a loop. And so these loops begin and end at our base point. Then we can define a binary operation star from two loops to a third loop. So star goes from pi 1 of X comma X naught cross pi 1 of X comma X naught to pi 1 of X comma X naught. And it's defined as follows. So given two loops gamma and gamma prime from the interval into X, we can define a third loop gamma star gamma prime from the interval into X as gamma star gamma prime of T for T between 0 and 1 is defined by, we do gamma of 2T whenever T is between 0 and 1/2. So note that for T between 0 and 1/2, 2T runs between 0 and 1. So we're getting this loop gamma from 0 to 1. And we'll define our third loop, gamma star gamma prime. When T is between 1/2 and 1, we'll do gamma prime of 2T minus 1. So note that this, when T is 1/2, right, this is gamma prime at 0. And when T is 1, this is gamma prime at 1. So what this does is run through the loop gamma and then gamma prime just a little bit faster so that it fits in the time from 0 to 1. So we can often call this operation concatenation, where we do one loop and then the other one. And this gives us a loop from that begins and ends at X naught still and maps the interval into our surface. Together with this binary operation, we will call pi sub 1 of X comma X naught the fundamental group of X. Since X is path connected, this group will be independent of our base point that we've chosen X naught in X. Given two loops A and B, we can take their commutator, AB of T, and again, what we will do is do a concatenation operation. So we'll take a of 4t for the first segment of time, b of 4t minus 1, then a of 3 minus 4t, and b of 4 minus 4t. So as in group theory, we sort of want to think of doing A, B, A inverse, B inverse. Let's do some examples. So first, take the case that X is P1 of C, or the Riemann surface. So let's consider the fundamental group of X based at X naught. So in the picture, you see that we've drawn one loop around the sphere at the equator, and it's based at this point. Okay, so now we'll consider this loop up to homotopy, which means that we're allowed to continuously deform this loop. And so that's what's illustrating. So we have our loop, and if we continuously deform it, we see that we can stretch it over the top of the sphere and then start to shrink this circle smaller and smaller until we get just this point. So what this diagram shows is that this loop drawn around the equator is contractible. So it can be homotope to a point. And the claim is that, in fact, any loop on the sphere can be contracted to a point. So that says that the fundamental group of the sphere is the trivial group. Let's consider another example. So now let's take X to be an elliptic curve over C, which we know we can write as C modulo a lattice lambda. The claim is that the fundamental group of X based at a point X naught is isomorphic to this lattice lambda, or we can write that as the group generated by elements A and B with the relation that their commutator AB is trivial. And so this group is isomorphic to C squared. So here's a picture. The point P is our base point X naught. And we could take our two loops, A and B. One is a longitude and one is a meridian of our torus. And what we see is that A cannot be contracted down to a point. So A, no matter how we deform it, will be a non-trivial loop. Similarly, B, no matter how we deform it, will be a non-trivial loop. And A and B, no matter how we twist it around the torus, will not be equal to each other. However, there is a relation between A and B, and that is if you do A followed by B, followed by A inverse, followed by B inverse, that loop altogether will be contractible. So that gives this relation that A and B commute. Next, we have the following proposition. Let phi from S1 to S2 be a non-constant morphism with capital N equals the degree of phi between compact connected Riemann surfaces. So we'll denote as Q sub 1 through Q sub little n in S2 the branch points of phi, so that the pre-image phi inverse of this set, Q1, Q2 through Q sub little n, in S1 are the ramification points of phi. Let's denote the complements as the subsets S equals S2 minus the branch points, Q1 through Q little n, and capital Y to be the complement S1 minus phi inverse of Q1 through Q little n. So take the surface S1 and remove the ramification points. Then these are non-compact connected Riemann surfaces such that phi from y to x is an unbranched cover, i.e. the ramification indices e sub p are 1 for all p in x. So if we look at the number g, let's let that be the genus of x, and that's equal to the genus of S2. Let's denote by gamma sub alpha from the interval from 0 to 1 into x, a counterclockwise loop around q sub alpha in S2. Then there exist two g loops, a sub alpha, b sub alpha, such that we have the fundamental group. So pi 1 of x spaced at x naught is equal to the group generated by a1, b1 up to ag, bg, and generated by gamma 1 up to gamma sub little n, with the following one relation. So we take the product over all I equals 1 to g, a sub alpha, b sub alpha, where alpha is running from 1 to g, times the product of beta equals 1 to n of the gamma sub betas. And so that relation is trivial. So this group is isomorphic to F sub r, the free group on r equals 2g plus n minus 1 generators. So we have our initial 2g plus little n generators, but then we have this one relation. So our group will end up being the free group on r generators. We will use this to construct a finite group called the monodromy group of phi inside the symmetric group on capital N letters from the unbranched cover phi from y to x. So let's consider an example. Suppose that little r is 0, then the genus of S2 is 0, and n is 1. So this case corresponds to taking the Riemann sphere, S2 is P1 of C, punctured at Q1 equals infinity. So our x is S2 minus Q1, and so that will be just C, the complex plane. Indeed, if we study pi 1 of x spaced to x naught, we'll get the trivial group for any complex number x naught in C. So this time we're taking the fundamental group of the complex plane, and in the complex plane, all the loops are contractible. Okay, now let's consider a second example with r is 1. Now genus of S2 is 0, and now little n is 2. So now in this case, we're taking the Riemann sphere S2 is P1 of C, but now let's puncture at 2 points. So one point will be Q sub 1 is the point 0, and Q sub 2 is the point of infinity. So now x, which is the complement, S2 minus Q1, Q2, is, well, we puncture our sphere at the point of infinity and at the point at 0, and we get the collection of non-zero complex numbers. And so now let's look at pi 1 of x based at x naught. So in this case, we'll get gamma 0, gamma infinity, such that gamma 0 times gamma infinity equals 1. So we get that we have loops going counterclockwise around 0 and around infinity, but in fact, these are inverses of each other. And so our group is isomorphic to V, the cyclic group where any integer n corresponds to the loop gamma 0 to the n of t equals gamma infinity to the minus n of t equals x naught times e to the 2 pi I nt. So as we said, gamma 0 and gamma infinity are counterclockwise loops around 0 and infinity respectively. Okay, now let's suppose that R is 2. Then either, first, the genus of S2 could be 0, and the number of punctures, little n, could be 3. Or the second case, we could take the genus of S2 to be 1, and the number of punctures, little n, to be 1. So in this first case, we're taking the Riemann sphere and puncturing it at 3 points. Let's take them as Q1 is 0, Q2 is 1, and Q3 is infinity. So we get that our x is S2 minus these 3 points, which is P1 of C punctured at 0, 1, and infinity, or the thrice punctured sphere. Now we can study this group, pi1 of x, based at x naught, and we'll get the group generated by gamma 0, gamma 1, and gamma infinity, such that gamma 0 times gamma 1 times gamma infinity equals 1. And again, we can view these 3 different loops as counterclockwise loops around 0, 1, and infinity, respectively, but we have a relationship between these 3 loops, right, that their product is trivial. Okay, now in the second case, we're considering S2 to be an elliptic curve punctured at 1 point. Let's puncture it at the point at infinity. So our x is equal to S2 minus Q1, or E of C minus the point at infinity. We can call this the puncture torus, and we have the group that pi1 of x based at x naught is generated by elements a, b, and gamma of the point at infinity. And so now we have a relation that a, b times a inverse times b inverse times gamma based at infinity is the trivial element. So this time we can view this element gamma based at the point at infinity as the counterclockwise loop around this point. These 2 groups are abstractly isomorphic because we can write down explicit maps between them. Now we'll consider monodromy. Let phi from S1 to S2 be a non-constant morphism with capital N equals the degree of phi between compact connected Riemann surfaces. So let's again let Q1 through Q little n in S2 be the branch points, and take the pre-image of that set, phi inverse of Q1 through Q little n in S1, the ramification points, and let x and y be the corresponding complements. So recall that x and y are non-compact connected Riemann surfaces, such that phi from y to x is an unbranched cover. So we have the following proposition. Let's fix gamma in pi1 of x based at x naught. For each alpha, there's a unique path, gamma tilde sub alpha, from 0, 1 into y. So think of this path living upstairs, such that now we're going to take our map phi and compose that with gamma tilde alpha. And so we're going to project this upstairs path, and when we project it down, will be our downstairs path gamma. So phi composed gamma tilde alpha equals gamma, and gamma tilde alpha of 0, so its base point, is this point p sub alpha. Okay, next let's consider the following definition. Since x naught is gamma of 1, which is also equal to phi of gamma tilde sub alpha of 1, we see that gamma tilde sub alpha of 1 equals p of sigma of I for some permutation sigma in the symmetric group on capital N letters. Hence, we have a well-defined map phi star from pi 1 of x comma x naught to s sub capital N, which sends our loop gamma to this permutation sigma. So some facts, this actually is a group homomorphism, and we call this the monodromy representation. The image monodromy of phi in S sub capital N is called the monodromy group, and the finite group aught of phi, which is the set of sigma in aught of S1, such that phi composed with sigma equals phi, are called the deck transformations. So here's an example. If genus of S1 and S2 are both 0, then S1 and S2 are both the Riemann sphere. And the automorphisms of S1 is isomorphic to PSL2C. So if we let beta from S1 to S2 be a morphism, then the automorphism group of beta will be a subgroup of one of the following from before: the cyclic group of order n, the dihedral group of order 2n, A4, S4, or A5. Next, we have the following proposition due to Felix Klein in 1888. So we have the following R belly maps with their monodromy of beta is equal to the automorphism group of beta is equal to the triangle group delta M and K. So for example, if we take x to the n, then this will have degree little n, and the triangle group is delta of n, 1n, which is the cyclic group of order n. For an example, giving our monodromy group the dihedral group of order 2n, we could take this belly map. Also, we can do examples for S3, A4, S4, and A5. So in the exercises, we saw all of these isomorphisms as parts of problems. But in this theorem, we see an example of a belly map in each case such that the monodromy group is this triangle group.